Thank you to our sponsors. Welcome to Future Forward, Artificial Intelligence, General Intelligence, Superintelligence. Today we're diving into a critical but often overlooked aspect of artificial intelligence, its energy consumption. Is the pursuit of ever more powerful AI models sustainable, or are we headed for an energy crisis? It's a question that's becoming increasingly urgent. The AI revolution is here, but it's not just about algorithms and data anymore. It's about electricity, cooling systems, and the very real-world limits of our planet's resources. We're talking about something beyond just the environmental cost. It's about economic competitiveness, geopolitical strategy, and even social equity. The way we approach AI development in the next few years will determine who benefits and who gets left behind. So let's start with the basics. What's driving this surge in energy demand from AI? For years, the mantra has been, bigger is better. Larger models trained on more data and with more computing power consistently outperformed smaller ones. This has led to an arms race, pushing AI labs and tech giants to build ever more massive systems. But there's a fundamental problem. Electricity, cooling, the physical infrastructure needed to support these models. We're hitting the limits of what's available, and it's forcing a rethink. By 2030, data centers globally are projected to nearly double their electricity demand. In some countries, AI data centers alone could consume 10 to 12% of the national electricity supply. That's a staggering figure. So the old approach of just throwing more compute at the problem isn't going to cut it anymore. We're moving into an era where efficiency is paramount. It's not just about how much raw power you can muster, but how effectively you use it. That's where metrics like tokens per watt come in. So you might be asking, tokens per watt? What exactly does that mean? Well, think of it as a measure of AI productivity per unit of energy. It tells you how many useful pieces of information, tokens, a system can generate for every watt of electricity it consumes. There's also tokens per flop, which measures tokens produced for each floating point operation, that is, computation. And unlike raw flops, these metrics reflect actual delivered intelligence. It's a more holistic way of evaluating AI performance, taking into account not just the output, but also the input, in this case, energy. It combines model architecture, hardware and infrastructure efficiency into a single standardized metric. It allows you to compare different models and providers on a level playing field, aligning AI development with the realities of energy consumption. Why, here is another question. How much of the energy consumption comes down to data centers and the physical hardware? Well, it's a huge factor. Data centers are energy hogs, especially with the accelerators and cooling systems needed for AI workloads. And it's not just electricity. Water consumption is also a growing concern, especially in drought-prone areas. Some hyperscale data centers use millions of litres of water daily. That raises the stakes considerably, doesn't it? We're not just talking about carbon emissions, we're talking about potential conflicts over scarce resources. And then there's the concentration of semiconductor manufacturing capacity, which creates supply chain vulnerabilities. Compute and energy are becoming strategic assets, and access to them will increasingly determine who leads in the AI era. It sounds like we need a multi-pronged approach to tackle this challenge. What are some of the key areas of innovation that can help increase tokens per watt? Well, there are several. On the hardware side, we're seeing next-generation accelerators that pack more computing power into each watt. We're also exploring things like wafer-scale chips, high-bandwidth memory, and even analog and photonic computing, which offer the potential for massive efficiency gains. There is so much innovation happening at the chip level. It's a hotbed of activity. But it's not just about hardware. Algorithmic efficiency is equally important. Techniques like mixture of experts, quantization, and distillation can significantly reduce the amount of computation needed per token. Mixture of experts is basically about only activating a small part of a neural network for any given task, instead of the whole thing. Quantization reduces the precision of the numbers used in the model, which slashes compute cost and memory bandwidth needs. And distillation is about creating smaller, faster models that mimic the performance of larger ones. So it's about being smarter with the algorithms themselves, rather than just relying on brute force. There are also system-level optimizations, like advanced cooling techniques, better batching and scheduling of tasks, and siting data centers near renewable energy sources. All of these contribute to a higher tokens per watt ratio. It's a complex puzzle, with no single silver bullet. Before we dive deeper into the solutions, let's reiterate the central point. We're talking about a fundamental shift in how we think about AI development. It's no longer just about model size, it's about energy efficiency. And this shift has profound economic and geopolitical implications. Countries with abundant low-carbon energy, strong semiconductor industries, and supportive regulations will have a distinct advantage in the AI race. This raises the question of equity. What about regions that lack these advantages? Regions without stable grids or access to affordable energy risk being excluded from the benefits of AI. We could see a further widening of the digital divide, with some countries becoming AI haves and others AI have-nots. So it's not just about access to the technology itself, but also the resources needed to power it. And you might be asking, how are the geopolitical implications playing out on the world stage? We're already seeing increased competition for power, land, water, and data center permits. Countries are starting to view compute and energy efficiency as national strategic priorities. There's a growing recognition that AI leadership depends on securing access to these resources. It sounds like we're heading towards a new kind of resource war, but it's not just about conflict. There's also the potential for cooperation. Decentralized compute markets are emerging, which could allow smaller players to monetize unused GPUs and participate in the AI ecosystem. But those will only partially offset the dominance of the hyperscalers. Let's switch gears and talk about the environmental and societal impacts. We've touched on energy and water consumption, but what are some of the other key concerns, I hear you ask? One of the biggest is the risk of undermining decarbonization goals. If AI growth leads to increased electricity demand that's met by fossil fuels, we'll be taking a step backwards in the fight against climate change. One paper I read states, AI growth must align with national decarbonization goals. Otherwise, increased energy demand risks pushing grids back toward fossil fuel baselines, undermining emissions targets. This is a critical point. It's not enough to just focus on AI efficiency. We need to ensure that the energy powering AI is clean and sustainable. And then there's the social permission to operate. The public will demand transparency regarding AI's energy, water, and emissions. If AI is seen as a resource hog with little social benefit, we're likely to see a regulatory backlash. Transparency is key. How can governments and policymakers ensure that energy efficiency is integrated into AI policy? Well, there are several things they can do. They could require energy and water usage reporting for major AI training runs, mandate the use of tokens per watt and tokens per dollar metrics for AI services, and forecast electricity demand and grid impact for hyperscale deployments. Think about this as setting clear standards and holding AI developers accountable. Policymakers could also set minimum efficiency baselines, require environmental impact assessments for large-scale model training, and provide incentives for energy-efficient facilities and algorithmic research. We also can't forget the role of civil society. Independent audits of AI energy usage, advocacy for equitable access to AI in developing countries, and ensuring that communities impacted by data center siting benefit economically. A holistic strategy is what's required. Let's bring this back to a point I made earlier about metrics. Why is something like tokens per watt such an important development, you might be wondering? It's important because it focuses our attention. Previously, it was all about the biggest model, the most parameters, the highest compute, but that's like judging a car solely on engine size, not miles per gallon. It's a crucial corrective lens as we race ahead. So let's look at what some strategic recommendations for AI labs, governments, enterprises, and civil society. AI labs and hyperscalers should treat efficiency metrics as primary KPIs, architect models using techniques like mixture of experts and quantization by default, and co-develop grid and energy plans with utilities and regulators. Governments need to integrate AI electricity demand into national energy planning, require transparency in resource usage, and invest in upgraded grid infrastructure and renewable energy. Enterprises should evaluate vendors using tokens per watt and tokens per dollar. Use appropriately scaled models rather than defaulting to frontier models, and track AI's contribution to corporate energy consumption. And civil society should develop independent audits of AI energy usage, advocate for equitable access to AI for global South countries, and ensure communities impacted by data center siting benefit economically. Those are some concrete steps that can be taken to ensure that AI development is sustainable and equitable. We've covered a lot of ground here, from the energy demands of AI to the economic, geopolitical, and societal implications. As we head into the wrap-up, it's clear that the future of general intelligence hinges on efficiency. It's not about building the biggest, most powerful models at any cost. It's about building intelligent systems that are sustainable, equitable, and aligned with global energy and climate priorities. As the white paper concludes, the future of general intelligence will be determined not by sheer model size, but by how many useful tokens we can produce per watt. But what happens if we don't prioritize efficiency? What's the alternative future look like? A world where only a handful of powerful actors can afford to develop and deploy AI, where energy grids are strained to the breaking point, where water resources are depleted, and where the benefits of AI are concentrated in the hands of a few. It's a future we must actively work to avoid. The choices we make today will determine whether AI becomes a force for good or a driver of inequality and environmental destruction. The key insight here is that efficiency isn't just a technical detail. It's a fundamental constraint that will shape the entire trajectory of AI. And it demands that we change our perspective. For too long, assumptions about unlimited compute and energy have gone unchallenged. We now need to bake in efficiency from the start. This means thinking critically about the energy footprint of AI, demanding transparency from developers, and supporting policies that incentivize efficiency. It's about making sure that AI serves humanity, not the other way around. So, as we wrap up, the question I'd like to leave you with is this: how can we, as individuals, contribute to a more sustainable and equitable AI future? What actions can we take to promote efficiency, transparency, and responsible development? See you in the next episode.